Hi crew, we've been looking at rational expressions, so fractions that contain a variable in the denominator anyway, possibly the numerator as well. Today we're going to look at rational functions, so equations that involve a rational expression. And we're going to focus today on features of rational functions, and then in our next video we'll put those all together. So let's go ahead and dive in, and let's start with the definition of a rational function. So that should say rational. A rational function, it's a function that can be written as the ratio, right, which looks like a fraction of polynomial functions. So in a rational function, we should be able to write that as one fraction with a polynomial on the top and a polynomial on the bottom. And so as such, you have x to the n, where n would only be an integer. So only powers of x that have integer exponents. So let's look at some examples. So in my first example, I have f of x equals x squared minus 1 over 1 minus 3 over x. If it can be written as a rational function, then I should be able to write that as one fraction, which means I need a common denominator. So that would mean I would have to multiply this first fraction by x over x, which would give me x cubed minus 3 all over x. Right? So yes, that is a rational function. Right? We have a cubic polynomial on top, linear polynomial on the bottom. In B, we have this complex fraction, which, to simplify, we would multiply in order to divide out my inner denominators. So I would want to multiply by a square root of x and an x on top, a square root of x and an x on the bottom. Multiplying the tops together gives me a root x times x over, multiplying the bottoms together, right? We would distribute this to each fraction, and the root x's would divide out, giving us x, plus, when we distribute to the second fraction, the x's divide out, giving us the square root of x times the square root of x, which is the square root of x squared, or just x, as long as x is positive. So we can simplify that, and that gives us x root x over 2x. And our x's are common factors. They'll divide out, which gives me, right, for g of x, that gives me a square root of x, or x to the 1/2 over 2. This is not a rational function because my exponent on x is not an integer. Our next example is for h of x, which we can combine because these two fractions have a common denominator, and we get h of x equals 2x minus 1 over x plus 3. And that is a rational function. We have a linear polynomial on top and a different linear polynomial on the bottom. Finally, we have k of x, and looking at k of x, right, because we have a power with x in the exponent, this is not a rational function, right, because we have x in the exponent. So, if you're going to determine whether a function could be considered a rational function or not, you need to simplify to get it as one fraction. And if you have a polynomial on top, polynomial on the bottom, it's a rational function. Otherwise, it's not. So, that's our definition. Now, let's look at our end behavior. Okay, like with polynomials, we can determine the end behavior for the graph of a rational function by looking at the power function that is defined as the ratio, again a fraction, of the leading term of the numerator and the leading term of the denominator. That provides us, again, with what we call our end behavior model. So in this first example, I have f of x. In the numerator, I have a 4th degree term, the highest degree term on the top, and I have a 2nd degree term, the highest degree term on the top. So my end behavior model for f will be the ratio of 6x to the 4th, my leading term from the top, and 2x squared. I reduce that. 6 divided by 2 is 3, and x to the 4th divided by x squared is x squared. So my end behavior model is 3x squared, and we know that the graph of that end behavior model would be an upward facing parabola, which tells us that the end behavior is, right, positive infinity or up to the left, and positive infinity or up to the right. So again, I don't know what the graph looks like in the middle based just on that, but I do know at the ends it's going to be going up on both sides. For B, my end behavior model for R will be the leading term from the top divided by the leading term from the bottom, which is x over x, which is 1. So this limit's a constant, which brings up something extra that we're going to do, and we'll take care of that a little bit later in the notes. But all this tells us is that if my end behavior model is a constant, right, this is a constant, that we have a horizontal asymptote at y equals 1. So my function will be approaching 1 on both ends. For C, our end behavior model here will be the leading term from the top, which is 3x, divided by the leading term from the bottom, which is x squared. That is 3x, right? That's 1 minus 2 is negative 1. And we know the graph of that function looks like this, which says that my end behavior is going to be the end behavior of this, which is 0, right? And we have a horizontal asymptote here of y equals 0. So we have definition of a rational function, and we have finding the end behavior model and using that like we did with polynomial functions. All right, now let's talk more about horizontal asymptotes. So we have previously learned that if the limit as x goes to positive or negative infinity of a function is a constant, then we have a horizontal asymptote at y equals the constant. That is also true that if the limit of our end behavior model is a constant, then we have a horizontal asymptote at y equals that constant. Okay. Whenever that happens for rational functions, we need to do an extra step where we consider the value of the function, right, for large positive or negative values to determine if the asymptote's being approached from above or below. This is going to help us graph. Okay? So it doesn't tell us what the function does in the middle, but it tells it what it does at the end. So let's look at this example. I have f of x equals 2 over 3 minus x. This is a complex fraction, and we're going to simplify it by multiplying top and bottom by x, which gives us 2x on the top, and when we distribute across the subtraction, we get 3x minus 1. This is a rational function. My end behavior model for f will be the quotient of my leading terms, so that'll be 2x over 3x. The x's divide out, and that is 2/3. The fact that this is a constant, right, tells us that we have a horizontal asymptote at y equals 2/3. So when that happens, this is what we're going to do. Okay? We're going to do a little mini xy chart. So we're going to look at x, and we're going to look at f of x. And what we want to do is look at what this function is doing compared to 2/3 at its ends. So I'm going to take a large negative value for x, and I'm going to take negative 100, and then I'm going to take a large positive value for x. I'm going to take positive 100. Now in the scope of infinity, negative 100 and 100 aren't very big, but they're usually big enough to tell us what a function is doing at its ends. And we're going to take those numbers and we're going to plug them into, right, we're going to plug those in for x into our simplified rational function. So if I plug negative 100 in for x into the top, I get negative 200. If I plug negative 100 in the x for the bottom, I get negative 300 minus 1, so I get negative 301. And I want to take that number and I want to compare that to the value of my end behavior model, which was the constant 2/3. Well, 200 divided by 300 would be 2/3. 200 divided by something bigger than 300 is going to be less than 2/3. So what that tells me about my graph is that my function is going to approach my horizontal asymptote from below 2/3 on the left end. If we take 100 and plug it in, so we're going to take 100 and plug it in for x in our reduced form, we get 2 times 100, which is 200, over 3 times 100, which is 300 minus 1, which is 299. So again, if we were to divide 200 by 300, we would get exactly 2/3. If we divide 200 by something smaller than 300, we actually get a number that's bigger than 2/3. And since that number is bigger than 2/3, that tells us that on the right end, we're going to approach our horizontal asymptote from above 2/3. We'll put that together when we graph tomorrow. Let's look at our next example. So here I have g of x, and I'm going to start by forming its end behavior model. So my end behavior model for g is going to be the leading term from the top, which is going to be the product of the leading terms from each of these factors. Right? Take note that we've got a negative leading term in this last factor. If I multiply all those together, right, 4x times x times negative 2x, I get negative 8x cubed. On the bottom, my leading term is negative x to the 5th. I simplify that. Negative divided by negative is positive. I have my 8. X cubed divided by x to the 5th will be x to the 3 minus 5, x to the negative 2nd. If we consider the graph of this end behavior model, right, x to the negative 2nd is going to have a shape like this. And we know that there will be a horizontal asymptote at y equals 0. And the graph of g of x will behave like the graph of its end behavior model. So like this approaches that horizontal asymptote from above on both ends, so would my graph of g of x. Right? So only when your end behavior model is a constant do we need to do this little mini sign chart where we plug in a large negative and a large negative number and compare what we get with the value of that constant of our end behavior model. All right, now let's talk about zeros and vertical asymptotes. The zero, right, remember zeros give us, real zeros give us x-intercepts. The zeros of a rational function will happen where, right, the fraction equals 0. And a fraction will only equal 0 where the numerator equals 0, but the denominator does not. Okay, so let's start with that in this first example. I have r of x equals x plus 3 over x plus 2. And my zeros will happen when my fraction x plus 3 over x plus 2 equals 0. That fraction will only equal 0 if the numerator, which is x plus 3, equals 0, which happens when x equals negative 3. Now, as long as the denominator doesn't equal 0 when x is negative 3, so my denominator is x plus 2, and negative 3 plus 2 does not equal 0. So I know that we have an x-intercept, right, at x equals negative 3. Now, vertical asymptotes will happen where the denominator equals 0 and the numerator does not. So if I want to find my vertical asymptote for r of x, then I want to find where x plus 3 over x plus 2 doesn't exist, which is going to happen in a fraction when the denominator equals 0. So that'll be when x plus 2 equals 0, which is when x equals negative 2. Okay, now, that has to make the numerator not equal to 0. So in a check on that, if I take negative 2 in for x in the numerator, and my numerator is x plus 3, as long as that doesn't equal 0, and it doesn't, then I have a vertical asymptote at x equals negative 2. Okay, so there's another feature, vertical asymptotes and zeros. Now, we're going to look at our limit behavior at vertical asymptotes. So we're skipping the example in your notes for right now. And we already know that if we have a vertical asymptote at x equals some number, then our limit of our function as x approaches that number from either the left or the right side will equal positive or negative infinity, right? Where we have a vertical asymptote, our graph will either rise or will fall as we approach that vertical asymptote. To determine the behavior of the function as it approaches the vertical asymptote, we're going to consider the sign of the numerator and denominator, right? So we're going to focus on whether it's positive or negative for values of x close to k on either side. So we're going to do a little table here as well. So this is how it works. In R of x, we already know that there is a vertical asymptote where the denominator, x plus 2 equals 0, which is where x equals negative 2. So we're going to come in here and we're going to do a little table. So we've got x's and we have the value of our function, which is R of x. And we know that when x is negative 2, your function does not exist. So now I want you to think about a number line where if I put negative 2 in the middle of that number line, I want a number that is just to the left of negative 2 and to the right of negative 2. Keep in mind, 0 would be to the right of negative 2. Now I want to pick numbers that are really close. So I'm going to take this and I'm going to take negative 2.1, which is just to the left of negative 2. And then on the right, I'm going to take negative 1.9. And I'm going to take those numbers and I'm going to plug them in for x into my rational function, where what I really care about is not the number I get so much, but the sign of that number, whether it's positive or negative. So if I come in here and I take negative 2.1 plus 3, right, over negative 2.1 plus 2, since 2.1 is smaller than 3, negative 2.1 plus 3 is going to give me a positive value. On the bottom, I have negative 2.1 plus 2, and since 2.1 is bigger than 2, right, and it's negative, that would give me a negative. If I divide a positive by a negative, then I get a negative value. Right? And what that tells me is that to the left of negative 2, my function is going to approach negative infinity. It's going to go down. If we do the same thing on the right side, then we're going to plug negative 1.9 in for x, so I would get negative 1.9 plus 3, which is positive, and on the bottom I would get negative 1.9 plus 2, which is also positive. Positive divided by positive is positive, which tells me my graph is going up on the right. So without exploring more than this, if I were to do the graph of R of x, knowing that I have a vertical asymptote at x equals negative 2, this analysis tells me that on the left side, my graph is going to go down, and on the right side, my graph will go up as we get close to that vertical asymptote. Again, we will put all this together tomorrow. All right, let's look at another example. Here I have b of x equals 25 over x plus 2 times x minus 3 squared. This will have vertical asymptotes where its denominator, which is x plus 2 times x minus 3 squared, equals 0, which will happen both when x equals negative 2 and when x equals 3. So I have two vertical asymptotes. If we think about our graph, I've got a vertical asymptote at negative 2, and then I have another one at 3. So when we come in and do our table, we're going to have to make it a little bit longer. This is for f of x, where we're going to take one vertical asymptote, negative 2, and pick a number left and right of that, and then we're going to take our other vertical asymptote, which is 3, and pick a number left and right of that. So I'm going to take negative 2.1, which is farther left than negative 2. I'm going to take negative 1.9, which is just to the right of negative 2. I'm going to take 2.9, which is just to the left of 3, and then I'm going to take 3.1, which is just to the right of 3. We're going to take those numbers and we're going to plug them in for x into our rational function, again, thinking about the sign. So when we take negative 2.1, 25 is positive, so that's positive. On the bottom, negative 2.1 in for x, plus 2 is going to be negative, and then negative 2.x minus 3 is negative, but we're squaring that, which makes it positive. A positive divided by a negative and a positive will be negative, which tells us our graph is going down towards negative infinity as it gets close to negative 2 from the left. When we plug in negative 1.9, we get a positive from the 25 on top. On the bottom, negative 1.9 plus 2 is positive, and negative 1.9 minus 3, though negative, once we square it, is also positive. Positive divided by positive times positive is positive, so my graph is going up on the right side of negative 2. Right, so if we just kind of put that in on the graph, right, left of negative 2, we know our graph is going down. Right of negative 2, our graph is going up. Now, let's look at what happens at 3. So now we're going to take 2.9 and plug that in for our x's, and we get a positive from the 25 over 2.9 plus 2, which is positive, and 2.9 minus 3, which is negative, but we're squaring it and get a positive, and we get positive. So that tells us our graph is going up on the left side of 3, so it's going to go up. If we plug in 3.1 for our x's, we have positive over 3.1 plus 2 is positive times 3.1 minus 3 squared is positive, and we get positive again. So on the right side, it's going up as well. And so we know how our function is behaving close to its vertical asymptotes. We're going to add one more feature here. We'll come back and do this graph tomorrow. We're going to talk about holes. Holes, right, which is sort of a comfortable common name, is technically called a removable discontinuity. And they occur at values of x where both the numerator and denominator equal 0. That will happen when we have a factor that is repeated both in the numerator and denominator. Right? So the hole is a point. Where that factor equals 0 is the x-coordinate. The y-coordinate of a hole will be what we get when we plug in the x-coordinate into the reduced form of the function, so after we cancel. We plot holes, right, as open circles on our graph instead of closed dots. And once we've plotted those holes, then we can just focus on the reduced form of our function for the rest of the graph. So here's an example. I've got h of x, which is a quadratic polynomial on top, linear on the bottom, and we're going to start by factoring this. So x squared plus x minus 2 will factor as x plus 2 times x minus 1. My denominator is x minus 1. Okay. We have a hole, right, where we have a common factor, numerator and denominator. Right? We have a hole produced, and that hole is going to happen where that repeated factor equals 0, which in this case will be x equals 1. So I know that I have a hole at the point 1 something. To find the value of that y-coordinate, we're going to do the reduced form of h, which we get by dividing out this common factor, which gives us x plus 2. We're then going to plug in the x value where we have this hole, so we're going to plug 1 into the reduced form of h, which gives us 1 plus 2, which is 3. And that gives us the y-coordinate of our hole. So if I were graphing this function, I know that at the point 1, 3, there's going to be a hole. Right? After that, the rest of my graph will look like the graph of x plus 2. Well, we know that y equals x plus 2 is a line with a y-intercept of 2 and a slope of 1, which would take me up to this point and would go like this. Right? So this rational function actually looks like a line with a hole in it. So we're going to stop there on these features. You've got work to do on a Google form that will be listed in the description on this video, and then we'll put everything together tomorrow in drawing great graphs of rational functions without a lot of very difficult work.